So after looking at the derivations of the variational inference algorithm, let's look at 3 different examples on how this can be applied to infer the posterior of the latent random variable conditioned upon a set of observed random variable. Note that this z over here, it can represent a joint set of the latent random variable as well as the set of unknown parameters. So now in the first example, we'll look at the case of a univariate Gaussian, where we are given a set of data denoted by d equals to x1 to xn, where this x1 to xn here is a set of n observations from the samples drawn independently from a Gaussian distribution, from a univariate Gaussian distribution. So the goal here is to infer the posterior distribution of the Gaussian distribution, which is parameterized by a mean mu and a precision tau over here, where we'll now use the precision denoted by tau as the inverse of the covariance. So previously we were looking at the sigma square. Now tau here simply denotes 1 over sigma square. Despite the difference here, the univariate Gaussian will still remain the same in the distribution space. The likelihood now is then given by this equation over here, where we d, which is all our observations conditioned upon the unknown parameters. So the example, this particular example here, is an example where we are going to look at the given a set of observations here. We are going to look at how to infer the unknown parameters, where the probability distribution here is given by the Gaussian distribution as written in this particular expression here. Now, the next thing that we need to define would be the conjugate prior distribution for mu and tau, where mu is our mean and tau is our precision matrix in the Gaussian distribution. So we'll use a normal distribution as given by this expression over here to denote the conjugate prior of the mean of this univariate Gaussian distribution, and it's conditioned upon the precision matrix given by this expression over here, where mu naught and lambda dot naught here, they are both hyperparameters denoting this particular conjugate prior distribution. And here tau, which is our precision matrix, the conjugate prior distribution is taken to be given by the gamma distribution, parameterized by 2 hyperparameters a naught and b naught over here. And this expression gives the gamma distribution in terms of tau a naught and b naught. And we can see that a naught and b naught are hyperparameters. If we give a different setting, we will see that we will have different distribution for the precision matrix in our univariate Gaussian distribution. Now, note that this is actually a very simple problem that can be found exactly using our maximal likelihood or maximal a posterior methods that we have seen in the earlier lecture, which means that we can either directly do this x condition upon theta, where this is simply equals to x1 all the way to xn, and condition upon mu and tau over here. And we know that by assuming IID observation here, we can simply rewrite this into x1 condition upon mu tau all the way until xn condition upon mu and tau over here, and we'll simply do a argmax of these likelihoods over theta, or in this case here we'll argmax it over mu and tau, and we can see that this can be computed in a closed form or in an exact expression where we can derive the analytical expression for mu as well as tau that optimizes this particular expression over here. Or otherwise, we can also do the same thing to do the argmax over theta, and we'll simply do the maximal a posterior of this guy over here, where we can use the Bayes rule to express this in terms of the likelihood and the conjugate prior. But for illustration purpose on how to use the variational inference to solve such problem here, where we'll simply treat this guy here, stated here as our set of latent random variables, which in terms gives us this particular expression, which is our familiar posterior distribution here. So we'll pretend that this is a very difficult expression to solve, which we cannot solve analytically. Now we'll look at how to actually use the variational inference to solve this particular problem here. We'll consider a factorized variational approximation to the posterior distribution given. So as mentioned earlier, that we'll use the mean field theory or the mean field approximation in order to approximate our target distribution of z condition upon x here. And we know that now this z here is going to be our mu and tau condition upon all the observations, all the observed random variables that we have, and we are going to approximate this using this target or the proposal distribution of q, mu as well as tau. And we know from the mean field approximation theory that we can redefine this particular proposal distribution, which is a joint distribution of mu and tau, into a factorized form of q mu and q tau. And this is recall that this is our mean field approximation theorem, where we simply can split z, our latent random variable, into a disjoint sets of zi's, and hence we can rewrite this expression here into this particular factorized form here. And we also know that after we have derived the optimal solution that maximizes the lower bound or minimizes the KL divergence between the target and the proposal distribution, we know that the optimal factor of this q over here of our target distribution or the proposal distribution here is simply given by the generalized form of the generalized result in this expression over here. This is the q star that optimizes or maximizes the lower bound and minimizes the KL divergence, which means that this guy here is the best approximation of our posterior distribution that we wish to infer. So starting from here, we will be able to directly get the result. And what's interesting here is that we would not make any assumption on the particular expression or the particular parameterization of q, and we'll just treat it as a functional form, which we'll see that the final expression of q's will automatically manifest itself from the joint distribution here. Now, the optimal solution for q mu can be obtained from this particular expression here, since we assume the mean field approximation theorem, where q of mu and tau can be simply approximated by q mu as well as q of tau here. So we will be able to find the optimal solution for these two terms over here separately. Let's look at the first term of q mu. The optimal solution of log q mu star here is given by the expectation of everything except for mu itself over the log likelihood of x and z. So in this case here, since we are interested in q mu, where mu is equivalent to our j here, so this means that we will have to take the expectation of everything except for mu, and in this case we only have two sets of these latent random variables, where the other one would be simply tau here. So we will take the expectation over the complete joint probability distribution of x and z here. So this guy here would be simply given by the likelihood mu and tau multiplied by our conjugate prior term that we have seen the definition in the earlier two slides, and taking a log here, we can see that it ends up to be two terms here. And substituting the expressions into this, we can see that we can pull out some of the terms of this Gaussian distribution, which is independent of mu, into the constant terms. So in this case here, we can see that this particular expression here, it contains all these coefficients that are independent of mu, so we can actually pull it out and dump it into the constant term over here, where what is remaining in this particular expression over here would be a function of mu, because what we are actually interested in is that we are interested in the functional form of q in terms of mu, where mu here would be our variable in this particular function of q mu. Now what's interesting here is that after we solve for q mu star over here, by simply taking exponential over both sides of this particular expression, where we can simply complete the squares of these two terms over here, and this gives rise to the expression of q mu taking a normal distribution where the parameters are mu n and lambda n inverse over here, which is given by these two terms over here. So we can also obtain a similar expression for q tau by substituting it into the optimal solution that we have seen earlier. And in this case here, we'll simply see that log of q tau, the optimal solution would be equals to the expectation of everything else, all the other latent random variables, except for tau itself, which is in this case just mu over the log of the complete joint probability distribution of x and z, which we can see that this is equals to the likelihood multiplied by the conjugate prior term. And we'll do the same thing. Since this expression over here is a functional form of tau, this means that whatever that remains inside this expression over here should be also a function of tau, and we can simply pull all the other terms into the constant expression over here, which finally we can evaluate it into this expression here. And now the next step, the final step that we need to do would be the same as the previous expression, where we need to take the exponential on both sides in order to get the optimal solution for q, the approximate solution for q. And we can see that by doing that, we'll end up with a gamma distribution here with the parameters of an and bn given by all the parameters that we have seen in this particular expression. And it should be emphasized that what's interesting here is that we did not assume any specific functional form for the optimal distribution q mu and q tau here. And what's interesting here is that they arose naturally from the structure of the likelihood and the corresponding conjugate priors. In particular, we can see that these two expressions over here, they are actually taking the same functional form as the conjugate priors that we have defined over them. So in this case here, we can see that we define the conjugate prior of mu here to take a normal distribution. And in this case here, q of mu, the end result of this would also be a normal distribution, which is similar to the conjugate prior expression that we have defined earlier. And similarly, for q tau here, we can see that it takes a gamma distribution, which is also similar to the conjugate prior distribution of tau that we have seen earlier. Now, for those who are sharp enough, by now you should have noticed that there is a problem in the solution that we have derived earlier, is that the solutions for q mu and q tau, they are actually coupled together. This means that there is no closed form solution for this proposal distribution of q mu and q tau. We can see that in the case of q mu, this is actually a normal distribution over mu n and lambda n inverse, where mu n and lambda n inverse is a function, especially this guy over here, lambda n here is a function of the expectation over tau. So this simply means that it has to be a summation over tau q tau on tau itself, and this means that there's no closed form solution for q mu over here, since it's a function of q tau. Similarly, for q tau over here, we can see that although it's a gamma distribution, the hyperparameters or the parameters of this gamma distribution, an and bn here, we can see that bn here, it's a function of q mu, where because in these terms here we see that it's an expectation over mu multiplied by a function over mu over here. So what this means is that we are going to take a summation over all possible mu's and q of mu multiplied by these particular terms here. So the way to overcome this problem is simply to do an iterative approach, as we have seen in the EM algorithm. We'll simply make an initial guess for the expectation over tau and then use this to compute q mu at first. So this guy here is simply the expectation over q tau, and then we'll make use of this initialization to compute this proposal distribution of q mu. Next, we'll use the revised q mu in the first step here to extract the moments of the expectation of mu and expectation of mu square, and use this to recompute q tau, as in this particular expression over here, which involves the expectation, the first and second moment of mu. And then once we have successfully computed q tau here, we'll then use this q tau to extract the moment of this expectation over tau and use this to recompute q mu again. So this will be iteratively back to the first step. And then we'll repeat these two steps here until we see no significant changes between the probability distribution of q mu as well as q tau. Now here's an illustration of how the proposal distribution changes with respect to the number of iterations that we have in the variational inference approach. Here we can see that the blue curves here, it's the distribution given by q mu multiplied by q tau. So this guy here is our proposal distribution, and the target distribution, which is the true posterior distribution of mu and tau conditioned upon all our observations, are given by the green curves over here. So after we have initialized the approximation of q mu and q tau, we see that this is given by the first figure over here. Then in the next iteration, we will estimate q mu from the expectation terms of tau, and we can see that after refining q mu, the blue curves, which is our proposal distribution of q mu multiplied by q tau, it's going closer to our target distribution, which is the green curves over here. Then in the next step, after we have re-estimated the q mu, we'll use it to update or re-estimate q tau here. So in this case here, we'll keep q mu fixed and update q tau, and we can see that after updating q tau, the blue curves here move even closer to our target distribution, which is given by the green curves here. And finally, at the convergence, we can see that this particular red curves over here will represent q mu and q tau, which is our proposal distribution, and it's quite close to the target distribution. And as usual, we can see that because this guy here, we are using the reverse KL divergence, which tend to underestimate the true distribution or the true posterior distribution. Hence, we can see that these regions here are not estimated well from our proposal distribution of Qs. Now let's look at another example, a slightly more complicated example of the mixture of Gaussian distribution, which is where the graphical model is given by this example here. So this is what we have seen in the lecture of the EM and the mixture of Gaussian distribution. And here, where X here represents all our observations, the individual observation, and Z here represents the latent random variable that tells us which cluster or which assignment that Xn should belong to. And pi here represents the mixing coefficient, which is to parameterize the categorical distribution of Z, our latent random variable. And lambda and mu here represents the precision or the inverse of the covariance and the mean respectively. Now, as what we have seen before in the previous lecture, for each observation we have a latent random variable Zn, which consists of the 1 of k binary vector with elements of k equals to 1 all the way to k. And in this case here, it simply represents znk when it's equals to 1. It simply represents that the random variable, the observations here, xn, is going to take the kth class. The conditional distribution of z given the mixing coefficient is given by this categorical distribution. This is what we have seen in the earlier lecture. And where the prior distribution or the conjugate prior distribution of pi, the mixing coefficient here, is simply a Dirichlet distribution over this mixing coefficient parameterized by the hyperparameter of alpha 0 over here. And for simplicity, we'll simply choose the same hyperparameters for all components over here. Hence, we only have alpha 0. The likelihood is simply given by the normal distribution over here, where we have one normal distribution for each component in the mixture of Gaussian distribution. Now, the conjugate prior of mu and lambda would be given by the Gaussian Wishart prior over here, which is in this expression over here. And this is the Gaussian Wishart prior consists of two terms. The first term is our normal distribution, and the second term would be our Wishart distribution, where m naught, w naught, and v naught here are all hyperparameters for us to parameterize the Gaussian Wishart prior for mu and lambda. Now, the joint distribution can be given by this expression over here. After we have defined the conjugate priors, the likelihood, as well as the posterior over the latent random variable of z. And what happens here is that, as we have mentioned earlier, that in the case of EM, we simply treat the latent random variable and the unknown parameter separately. So in this case here, z would be this guy over here, and theta here would be pi, mu, as well as tau. But in the case of variational inference, we don't differentiate between the unknown parameters and the latent random variable. We simply lump all of them together. Hence, what we are interested in would be to simply find the posterior distribution of z, pi, mu, lambda conditioned upon x. And all these here are treated as our latent random variable. As a result, in our derivation of the variational inference, we say that we are going to use the mean field approximation to approximate this posterior distribution, which can be intractable, where there's no analytical form that exists, or it could be computationally very expensive to compute. Of course, this is also a toy example, because we've seen that we can easily solve this using the EM algorithm. But let's pretend that this is going to be a very difficult posterior distribution to be expressed analytically or to be computed in a tractable amount of time. Now, what we want to do would be to simply come up with a proposal distribution over all the latent random variables of z, pi, mu, and lambda. We want to make use of this to approximate this posterior distribution here. And we have seen that according to the mean field approximation algorithm, this joint distribution here, this proposal distribution here, can be factorized into two forms over here, two factors over here. We'll define the first term here to be q of z, as well as the second term to be the proposal distribution over all the unknown random variables or unknown parameters of pi, mu, and lambda here. And what's interesting here is that even though we define this factorization form to be these two terms only, we can see that later on, as the solution of variational inference in the functional form, you will automatically tell us that these terms over here can be factorized even further, even though right from the beginning we didn't make that assumption, or we didn't know this assumption. We simply do this factorization only, and we can actually see from the graphical model that pi, lambda, and mu, they are independent. So we can think that this particular term here could be just q pi and q of mu and lambda, since these two sets of unknown parameters, they appear to be independent in the graphical model. But now in order to illustrate the power of variational inference in the functional form, let's just pretend that we do not know this, and here we simply do a factorization in this particular form here, and but nonetheless the result of the variational inference will show that you will automatically turns out to be in this factorized form of qz multiplied by q pi and q of mu and lambda. So as usual, let's loop through the different factors in the proposal distribution. The optimal solution for qz would be given by this expression over here, where now we are treating z here as j, and we will take the expectation of all the random variables, the latent random variables, except for z itself, which in this case here would be pi, mu, and lambda over the joint distribution of x and all the latent random variables plus a certain constant. This is the expression that we have seen for the optimal solution that will maximize the lower bound in the variational inference. And substituting the joint distribution, which is what we known earlier, all the expressions that we have written in the previous few slides, and exsolving all the terms that do not depend on z. So here, since the solution is a functional form of the latent random variable of z, what we should do would be to factorize out all the parameters or all those factors that are independent of z into the constant term over here. And what we're remaining here would be simply the terms that are dependent on z. So we can see that there's z over here in these two terms, where the first term is the expectation over q pi and the second term is the expectation of over q mu lambda over here. Now substituting all the expressions that we have derived earlier for the likelihood as well as the conjugate prior into the joint distribution, now we can obtain this qz, the optimal form of log qz, to be this expression over here, where log of rho here would simply be given by this complicated expression over here. I won't go through the derivations of this expression. I'll leave it as an exercise for you to do. And now taking exponential on both sides of the log qz, the optimal solution of qz, we can see that the final expression of q, of the optimal solution of q, is given by this expression over here. And we need to normalize this q star, z star over here with the partition function, which is simply given by the summation of over the numerator of rows over here. And now rewriting this expression with the partition function, absorbing the partition function and into R over here, we can see that now the optimal solution of qz is given by this expression over here, which has the same functional form as the categorical distribution of the posterior over the latent random variables of z. So here, what's interesting here is that, as mentioned earlier, that we did not specify the functional form of qz from the beginning, but the variational inference would automatically assign it a functional form. And what's interesting here is that this particular functional form of the random variable, of the latent random variable of z, will be the same functional form as the conjugate prior, or the prior term of that random variable, or that latent random variable. In this case, it would be z, and this we defined it to take a categorical distribution, which is exactly this particular form over here. Now, before we go on to solve the optimal solution for the proposal distribution on the latent or the remaining latent random variables, or the unknown parameters of pi, sigma, and tau, let us first define three statistics on the observed data sets evaluated with respect to the responsibility. So we are going to predefine nk, which is summation of all the rnks, where rnk is what we defined in the previous slide, as well as x bar k to be equivalent to this term over here. So this is similar to the expectation, but weighted by this rnk over here. And we are also going to define a covariance over here, which is simply the covariance term weighted by R and K. And the reason why we predefine these three statistics is that we want to make it such that it's analogous to the quantities that is evaluated in the maximum likelihood of the EM algorithm for the Gaussian mixture model. And we'll see how this is used in the subsequent slides when we derive the optimal expressions for Q over the mixing coefficient, the mean, as well as the precision matrix. So now this is given by this particular term here, the optimal of Q over these three unknown random variables or three unknown parameters of the mixture Gaussian distribution is given by the expectation over all the other random variables or all the other latent random variables except for pi, mu, and lambda. And in this case here would be the expectation over z on the log probability of the joint distribution here. And we can see that by substituting these terms over here from our graphical model, given by the likelihood as well as the conjugate prior terms, we can get to these particular expressions over here. And what's interesting here is that we can see that some of the terms here are only dependent on pi, which is these two terms over here, and we can collectively collect them together. And these two terms over here are dependent on only mu and sigma, and they are independent of pi. So again, those terms that are independent of pi, mu, and lambda, we will just factorize them and dump it into the constant term over here. And here, what it suggests here is that since we have four terms where two of them are dependent on only pi, and the remaining two are dependent on only mu and lambda, what this suggests here is that we can further factorize Q, mu, pi, and lambda into this particular form over here, where the factorization would be consisting of Q pi as well as a product of all the Q and mu k's as well as lambda k, which is shown in this expression over here, since it's a summation over k for both these two terms on mu k and lambda k. So this means that this expression or this proposal distribution can be further factorized into this particular form. Now we can further evaluate the optimal solution of Q pi by from the two terms that are related to this Q pi in the earlier slide, and taking the exponential of both sides, we can see that this ends out to be a Dirichlet distribution. This means that the optimal proposal distribution for Q pi is a Dirichlet distribution that is given by alpha, parameterized by alpha, where alpha here is simply alpha naught plus nk, where nk is what we have defined in the earlier slide. And similarly for Q, mu, and lambda, we can easily find this by taking out the two terms, the two respective terms that is dependent on mu and lambda in the earlier expression, and this is what we will get. This is a complicated expression over here, but it consists of that two terms that we have seen in the previous slide. And what's interesting here is that this guy here is the conjugate prior, which is the normalized Vis-Hart conjugate prior that we have defined in the previous slide. And now we can merge these two terms together since they are both normal distribution. And then after that, we'll derive the expression for the optimal solution of mu and lambda for Q by taking the exponential on both sides of this particular equation over here. And what we can see that is that we'll finally obtain this expression over here, where this is a exponential of the merging of the two terms, of the two normal distribution terms that were seen in the previous slide. And what's interesting here is that we end up to be having an expression of Gaussian Vis-Hart distribution for the optimal solution on the proposal distribution over mu k and lambda k. And this is again what we have mentioned very early on, that we did not specify any functional form of Q, but it turns out that this is manifesting itself in the form of the prior or the conjugate prior over these latent random variables that we have defined in the graphical model. And this is the same case when we look at this particular proposal distribution over the mixing coefficient. It has the same distribution as the conjugate prior over the mixing coefficient. Now, similar to what we have seen before, all the solutions of the proposal distribution over the latent random variable as well as the unknown parameters are coupled together. And we'll use the iterative approach to resolve this problem. And what's interesting here is that we'll see that the iterative approach is similar to the EM iterations, despite the fact that we are using variational inference to solve for this mixture of Gaussian model. So in the first step, we will solve for the optimal solution of Q of Z here. And in this case here, we can see that the optimal solution is given by this equation over here, which depends on Q of pi, mu, and lambda. And we'll first initialize Q, pi, and lambda over here in order for us to solve for this QZ. So in this case here, this is equivalent to the expectation step, or the E step that we have seen in the EM algorithm, where this guy here, the initialization over here, would be simply equivalent to theta O. And what we are actually solving over here would be Q of Z, and this is equivalent to the posterior of Z condition upon X theta O here. So once we have solved this in the expectation step for the posterior distribution over the latent random variable of Z, the next thing that we do in the EM step would be to do the maximization over the unknown random variables. And in this case here, this would be equivalent to the M step. So in the M step, we are going to take the maximization over the and in the M step, we are going to take the maximization over the complete log likelihood on the evaluated on the posterior distribution of the latent random variable. And we can see that this is exactly the same, or this is equivalent here, where now we are having a distribution over pi, mu, and lambda here. So this guy over here is equivalent to the expectation over the complete log likelihood on the distribution of the latent random variable. So if we were to maximize this guy over here, these expressions over here over pi, mu, and lambda, this would be equivalent to having our unknown parameters in the maximization step over here. Now here's an illustration of the iterative steps in our variational inference approach on the mixture of Gaussian. We can initialize the number of clusters to be k equals to 6, but we'll see that it eventually converges to 2 unique clusters over here. And what this means is that all unused components would have respective R and K to be approximately equals to 0. And this is also one of the advantage of using the variational inference algorithm, because in this case here, it will simply mean that R and K converges to 0 for the unused components, and this is equivalent to model selection. So the last example that we'll see here is the Ising model, which we can make use of this to do the image denoising problem. This means that given this particular image over here, which is a noisy image, it's corrupted with some noise, what we want to do is that we want to recover the original clean image from this observed image, noisy image over here. And here we'll denote the observed random variable as y to be either -1 or +1. This is a binary state random variable which is either occupied or not. And then here the latent random variable here of the clean image would be also in a state of a binary state of -1 and +1, which will denote as x over here. So the graphical model here would be for every single latent random variable that is an observation which represents that pixel. So these are all the observed value per pixel. And so for every pixel here, what we want to infer would be the clean image, the state of that pixel in the clean image. And we can see that, as I have mentioned in many times in the previous examples, where I said that every pixel over here, they remain as neighbors not because of coincidence, because they are neighbors, because they are really affecting each other, or in the real scene, or they are really coexisting side by side in the real scene when they are projected onto the image. This means that neighboring pixels should be more likely to take the same label, to be taking the same class label. And in this case here, this means that for every pixel, the latent random variable that represents the clean image, for every pixel, what happens here is that we want it to be connected to its nearest neighbor. So all the 4 nearest neighbors should be connected with respect to that particular pixel. And now the joint distribution of this this graphical model here can be given by P of xy, which is simply equals to px multiplied by py condition upon x. So this is our likelihood. This is our likelihood distribution, where y here is our observed random variable, which is from the noisy image, and x here is our latent random variable, and this would be the prior term over our latent random variable here. Now the prior form would be this particular expression over here, where we simply use the Gibbs energy distribution to express the prior term over here. So where E here is the energy function that parameterize this prior distribution over our latent random variable. So what this means here is that this is actually following what we call the Ising model. And what this means is that in the case where xi and xj, where I here is one of the random variable in the pixel, so xi over here, and xj is its neighbor that is connected to it. So what we want here, as mentioned earlier on, that we want to enforce the prior, that these 2 neighboring pixel, they should take the same label. So as a result, what we want to do here is that if they don't take the same label, then we are going to penalize this. This means that the energy will increase if xi and xj do not take the same label. And if they take the same label, then we will decrease this particular energy term, which we can see here. So W here is simply a constant weight that or a constant cost that we assign to this energy value over here. So in the case of xi and xj are binary random variables, we would have 4 different combinations over here. So xi, xj, they can both be taking -1, and +1, +1, or -1, +1, and +1, -1 over here. So in this case here, what we want to do is that in the case where they are taking the same label, we want to minimize the energy. In the case where they are taking different label, we want to increase the energy given by E0 over here. And we can see that if both of them are taking the same sign, the product of these 2 states over here will end up to be +1 over here. So when it's +1, this term over here will become wij, and there's a negative sign over here, so this will become negative wij. And if they are taking different signs over here, the product of these 2 terms will end up to be -1 over here, and as a result, this will become +w. So this means that this will become +wij, and this will become -wij, which means that in the case where they are both taking the same label, I will have a negative or a lower energy level. And in the case where they are taking the different states over here, and then I will end up with an energy function that is positive of W, and this means that it's a high energy value. And what we want here is that taking the maximal likelihood or the maximal A posterior over the joint distribution, what we want to do here is that we want to maximize this probability, which in turns we want to minimize this particular energy function here. So what this means is that we want to encourage all the neighboring latent random variables to take the same state. But of course, if we were to simply optimize over these particular prior terms over here on the latent random variable, then we could end up to have a clean, the so-called clean image to be all taking the same state. So it could be all black or it could be all white if we only have the prior terms. So concurrently, in order to solve this particular problem, concurrently we also need the likelihood function to make sure that the states that our latent random variable is taking, besides it has to follow the smoothness prior that we have enforced here, it must also be close to what we have observed. That means that we do not want to lose the image despite that it's from the noisy image. We do not want to lose that particular form and in the end up with a smooth white or a black image. And hence we need to enforce the likelihood terms over here, which is simply also given by this equation over here in the Gibbs energy distribution. So we can say that this particular L1 here would take the similar form as E0 over here, where we want it to have a high energy value when they are not the same state, and we want it to take a low energy value when it's taking the same state as shown by this table over here. So now putting everything together, we have a joint probability distribution of this particular form here, where E here is simply given by the two terms. The first term, which is given by the Ising model, and the second term is given by our likelihood term, which can be defined to be similar to our Ising model. And hence, the log of the joint probability distribution is now given by this term over here, where this guy over here is simply the partition function. Now we'll see that the approximate solution of the latent random variables can be fully factorized into this particular approximation following the mean field approximation theorem. Now the log of the optimized factor is given by this expression over here, where we simply say that we are looking at the probability distribution over xi, the proposal distribution over xi, and this would be equivalent to the expectation of x or all the other pixels except for the ith pixel itself over the log of the joint probability distribution of x and y, both the observed random variables and the latent random variable, plus a constant term. And by substituting this guy over here from our graphical model that we have seen earlier, that consists of the prior term as well as this term over here, which is our likelihood term over here, and we will end up with this particular expression. And what we can see here is that since the expectation is taken over all the latent random variable except for xi itself, we can see that we can push this expectation term into this expression over here, where since these guys over here are xi is independent of all the random variable except xi itself, we can see that this expectation only acts on this xj over here and is independent of this guy and this guy over here. So as a result, we can rewrite the optimal solution for qi in this particular expression over here, where the expectation now is inside this mu j over here, because it's independent of this term is independent of xj, and this term is independent of xj as well. And here we rewrite this particular term as this term over here, which is equivalent to taking the expectation of this xj with respect to the expression of the distribution of qxj over here. And this is also equivalent to the mean value of the node j, because we are taking the expectation over the value of xj, and q here can be treated as the empirical distribution. So the results are coupled as before, and we'll do iterative update with an initialization of all the mu's. We can see that we can further define mi as the mean field influence on node I. So here we'll define this particular term mi equals to the summation of wij and mu j, which is simply from this particular term over here in the optimal solution of qxi. and then let's let L plus to be the term to denote the expression of L, the likelihood to be a positive state, and L minus when it's taking a negative state. So we can rewrite the solution into this particular form here, since Qi will take a distribution of xi equals to 1 and xi equals to -1, and substituting it into all these terms over here into the previous expression here, when xi takes the two different states, this would be the two different distribution that we can get. We can see that it's taking a sigma expression over here, or sigma distribution over here. And finally, once we have done this, once we have computed q of xi, we can update the new mean for the pixel I by computing this particular expression over here. Mu I would be equals to the expectation of the x over the distribution of the proposal distribution of Qi, and this is given by this particular expression over here, and we'll iterate between the two steps until it converges. So this is also why we call it a mean field approximation, because in this case here it clearly illustrates that we are first computing the mean of all the aggregated nodes, and then we use it to update the distribution, and we iterate between these two steps until convergence. Here's an example of how it looks like when we denoise this particular noisy image using the mean field approximation, or the variational inference approach. And after several iterations, 15 iterations, this is what we will get as a clean image. Now the last thing that we will look at is the Loopy belief propagation algorithm. So Loopy belief propagation algorithm is just a simple algorithm on the graphs with cycles. We'll look at that this is actually equivalent, simply equivalent to our max product algorithm. We'll simply adapt it to graphs with loops. It's actually a formal proof that Loopy belief propagation algorithm, despite its simplicity, it's from a variational inference point of view. And I won't go into the proof because this particular proof, it's proven in a 300 pages paper written by this Wainwright as well as Jordan, that is published in 2008. And if you are interested, you should look at the formal proof from that particular paper. So the idea is actually very simple. We'll just apply belief propagation, message passing, or the otherwise known as the sum of products algorithm to the graph. Despite that it has loops, we'll simply ignore the loops and treat it as like it is a tree, and we'll do message passing as usual. So the pseudocode for Loopy belief propagation on a pairwise Markov random field is given as follows. We'll first initialize all the messages with to 1, the messages from node S to node T as 1, as well as the belief on every node to be equals to 1. This is the probability distribution that we initialize everything to 1. So and the next thing to do would be we'll simply for every single node in the graph, we'll simply ignore the fact that there is loops. There are many loops in this particular graph. We'll simply treat it as a tree, and then compute the messages as usual. So in this case, we're looking at this particular random variable over here, which is xt, and we'll simply compute the messages that's passed to xt as usual. And this would be given by, since we are passing the message from xs to xt, then we better make sure that all the random variables of xs in the set of xs are marginalized out. Hence, we need to do a marginalization over xs, and we need to marginalize this over the unary potential of xs multiplied by the binary potential of xs and xt given by this term over here, as well as the product of all the messages that are coming into xs, and this is the terms over here. And then once we compute this message, we'll update the nodes simultaneously in this step. We won't wait for it to we won't wait for all the messages to reach the node or the root node of the tree in order to update this belief anymore. In this case, because we have a loopy graph, there's no notion of root node in this particular loopy graph. So what we'll do here is that after every time we pass a message into that random variable, we'll directly update the belief of each one of the nodes of that particular random variable. And we'll do this repeatedly until the beliefs don't change significantly. So one of the catch of this particular algorithm is that convergence is not always guaranteed, and sometimes this particular algorithm might not converge, where the beliefs will not stabilize and will not be able to terminate this particular algorithm. But in fact, in most of the practical application, this algorithm does work to a certain extent. And here we'll still have a message passing protocol as before, and in this case here it can be both synchronous or asynchronous message passing. In the case of synchronous message passing, we'll pass all the messages concurrently. We'll not wait until any messages to be all the messages to reach a certain node, but we will pass all the messages concurrently. This means that given the messages from the previous time step or the previous iteration, we'll concurrently update all the current message of mk over here at the current iteration with, for every single random variable, with the message that is computed from the previous time step. And there's also asynchronous message passing, where we can predefine a certain steps of passing the message. For example, in this case here, where we have random variable 1, 2, 3, and 4, we can define a tree that looks something like this, where we'll say that at the first level, we'll pass all the messages into 1, then after that, we'll propagate into 2 and 3 concurrently, and from 2 and 3, we'll propagate into 4, 3, and then 2 and 4, and so on and so forth until we reach the leaf nodes, and then we will terminate the particular loopy belief propagation algorithm. So in summary, we have explained the concept of variational approach. In particular, we derive the solution for the optimal Q or the proposal distribution that approximates the intractable posterior distribution that we wish to infer using the lower bound of the maximal likelihood and KL divergence. And then we make use of this variational inference approach to do inference on the graphical model that can contain both hidden random variable as well as the unknown parameters. Finally, we introduced the loopy belief propagation algorithm, which is a simple algorithm that can do message passing on a graph that contains loops.